Hello! Let's look at some Dijkstra spin-off problems. We will start with a very common scenario from everyday life. This wooden crate was suddenly dropped in the middle of nowhere. Inside that crate is our dear friend, Plebosaur. He quickly realizes that it's a Monday and he's going to be late for his minimum wage job. Furthermore, he figured out the one responsible behind this predicament is his evil manager. He's desperately looking for an excuse to fire the Plebosaur. He hopes this plan is enough to make the Plebosaur late for work. For the first problem, Plebosaur is trying to get to his first checkpoint, Ninja City, as quickly as possible. The problem looks very familiar, but this time there's a twist. Looking inside his back pocket, he finds he has access to a mysterious object, the Orb of Zero. He can use that to set the weight of any one edge in the graph to 0. This complicates things. How should he best use this orb? If you want to think about this problem yourself, pause the video right now. At first glance, this problem appears very tricky. It's not as simple as finding the shortest path and using the orb on one of the edges of that path. In this example, the best path using the orb is different than the best path without using the orb. A naive approach would be to set the weight of an edge in the graph to 0, find the shortest path in that graph, then repeat the same for every edge. This strategy would indeed find the shortest path using the orb, but it has a big problem. What's the time complexity of this algorithm? Well, this approach runs Dijkstra's algorithm for every edge in the graph. As a result, we get a very bad time complexity. There's something clearly problematic with running Dijkstra so many times. Surely, we can do better than that. Here's the idea that we will be using to solve this problem and many other problems in the future. We will run Dijkstra's algorithm just one time as it already is. We will not be making any changes to Dijkstra. We will only be modifying the graph. The way we will do that is adding more information to our nodes than just location. What do I mean by that? If I were to show you this graph, you would intuitively understand that Plebosaur is currently located at node 0. Also, each node's name is just its number. Let's change that. We now have two node number zeros, but we have added additional information. In one of them, we have used the orb, in the other, we haven't used the orb. This means that in this example, Plebosaur is located on node 0, but he hasn't used his orb. And in this example, Plebosaur is once again in node 0, but he has used his orb. Let's look at this on a real graph. In this example, we want to get from node 0 to node 3. This is what the new node names look like. As you can see, we have doubled the number of our nodes. Now we face the next problem. What should the edges of this graph be? Well, for the part of the graph where we haven't used the orb yet, the weights of the edges should be the same. If you move from node 0 to node 1 or 2, for example, without using the orb, then the cost of the travel is the same. Likewise, for the part of the graph where we assume that we have used the orb. This is where things get interesting. I have a question for you, and I hope this is when a light bulb has popped up inside your head. What edges should we add to this graph to connect the two parts of the graph to each other? Pause and think about this for a little time if you want to. If we look at node 0 with the orb, it has the option to spend the orb to travel to one of its children. We can represent that in our graph like this. To explain what you are watching, if you are in node 0 and you spend the orb, we can move to one of your children with a weight of 0. You spend the orb in the process, and we represent that in the graph by the fact that we move from a purple node to a red one. Doing the same with node 1 and 2, we complete our graph. But what does this have to do with anything? Well, if you think about it, the shortest path between node 0 and node 3 in the original problem is the shortest path between these two green nodes in this graph. This means that if we run Dijkstra on this graph, we can solve our original problem. To summarize, all we have to do to find the shortest path between node A and B is 1. Construct the modified graph, and 2. Find the shortest path between node A with the orb and node B without the orb. What's the space and time complexity of this algorithm? If the original graph has n nodes and m edges, then the new graph has 2 times n nodes and 3 times m edges. Then we run Dijkstra on that graph. This means that we have achieved the same complexity as Dijkstra's algorithm. As a result, not only have we found an optimal solution to this problem, it's also very, very easy to implement when you write code. Next problem! This time the plebosaur must cross Ninja City to get to the capital. This looks like a standard shortest path problem, but things are never this easy. His evil manager has hired some ninjas to make his life difficult. Some nodes in the graph contain ninjas! Plebosaur would rather avoid physical confrontation, so he cannot visit a node with a ninja on it. Nodes 1 and 4 in this case. That is, unless he picks up a crowbar first. Some nodes have crowbars. In this example, just nodes 5 and 3. If Plebosaur picks up a crowbar, then he can freely visit nodes with ninjas on them. This is because he's confident he can use the crowbar to peacefully resolve any potential conflict. For the sake of simplicity, let's also assume that a node can't have simultaneously both a crowbar and a ninja on it. I will now put the main idea we are working with today on screen, and I will give you a few seconds to think about it before showing you the solution. Time to solve it! First question we have to answer. What information should the nodes of our new graph contain? Simple. They will tell us whether or not we have picked up a crowbar. Let's see how this looks on our graph. This is the original graph. These are just the nodes. And these are the new nodes. All that's left now is adding the edges. For the part of the graph where we don't have a crowbar, we add all the edges of the original graph minus the ones to and from nodes with ninjas on them. For the part of the graph where we have picked up a crowbar, the edges are the same as the original graph, since we travel without any restrictions. The last thing to add is the ability to pick up a crowbar. We represent that like this. Nodes 3 and 5 have crowbars on them. This means that you can move from node 3 or 5 where you don't have a crowbar to node 3 or 5 where you do. The weight of the edge connecting them, of course, is 0, since the problem description didn't say picking up a crowbar takes any time. To find the answer to our original problem, all we have to do is find the shortest path between our starting node and either one of nodes number 6. We look at the two answers and compare them to get our final answer. In this case, the path to the bottom node number 6 is faster. Another way to implement this is to create an answer node and connect all the nodes we want to compare. As a result, now the answer to our original problem is the shortest path between our starting node and also node ans. Dijkstra will automatically find which of the node number 6s is responsible for the best path if we use this. This is a bit fancier. Usually the previous idea of just comparing both node number 6s is easier to implement. Now we have solved the second problem using pretty much the same solution we used for the first problem. Once again, this solution has optimal time complexity and a very easy implementation. Last problem! The plebosaur has successfully entered the capital, but his journey is not over yet. He must make his way to his workplace, Krusty Dino. Unfortunately, time's running out, and he can't hope to get there in time just by walking. He quickly looks at what vehicles he can use. The only dinosaur-compatible ones in the city are unicycles and scooters. They are located in some nodes in the graph. It's possible that a node contains both. Much like the crowbar from the previous problem, if Plebosaur finds himself in a node with a unicycle or a scooter, he can start riding that vehicle for as long as he wants. He can't simultaneously use both a scooter and a unicycle, but there is no limit to how many times he can switch vehicles. Riding a unicycle makes it so that he can travel edges with even weights at half the time. He can still travel edges with odd weights normally, but he doesn't get any bonus. Likewise, riding a scooter allows him to travel edges with odd weights at half the time, rounded down. Just like with the unicycle, he can still travel edges with even weights normally, but he doesn't get a bonus. If you want to solve this problem yourself, this is your chance to pause the video and think about it. Once again, we have to figure out what information we should store in our nodes. Hopefully, it doesn't come as a surprise by now that we will store which vehicle we're currently using. I will use just color coding for now to make the resulting graph a bit clearer. In the example graph we are looking at, this is what the new nodes look like. Now on to adding the edges. For the no vehicle part of the graph, the edges are identical to those in the original graph. For the unicycle part of the graph, we just have to make sure that we divide the weight of every edge of even weight by 2. Likewise, for the scooter part of the graph, we halve the weight of the edges with odd weights. Next step is we add the ability to pick up a scooter. We can see that with node 1s and nodes 2. They have the ability to travel to the scooter part of the graph. The same thing is added for the unicycles. You can move from node 4s or node 5s to the unicycle part of the graph, finishing this complete monstrosity of a graph. Now, to answer our original question, we have to find the shortest path between node 0 and one of node 6s. We just run Dijkstra to find the shortest path to each one of those individually and take the shortest one, which is this absolute beast with a total weight of 7. Congratulations! With your help, the Plebosaur got to his job in time, much to the disappointment of his manager. I hope by now you have realized what these 3 problems Plebosaur's manager created for him are. Not 3 unique problems, but rather a pathetic attempt to disguise the same problem with 3 different exteriors. At the same time though, the essence remains the same. This is a technique he stole from the entertainment industry. That's all I have for today. Give me any feedback if you have anything. I hope you had some fun. I hope you learned something. Thanks for watching.